Okay, good morning, everyone. Just okay, I want to start with a few announcements. The first one is that I posted a quiz assignment online on Pearson system, labeled titled as Quiz Zero. Very simple assignment, like just 2 or 3 questions. Shouldn't take more than like 5-6 minutes of your time. But the purpose of the assignment is so that students get familiar with the online submission system. Typically, you might be used to scanning your documents or your assignments and uploading to Canvas, right? During the pandemic, everybody did that. And I also continue to do that for my in-person classes. But this is a new feature that has just come up recently. And so I'm going to implement this for my classes. So after every quiz in class, what I do is there is a work time. So if it's a 15-minute quiz, let's say it's scheduled for 10 a.m. in the morning. We start at 10 a.m. You have 15 minutes to work on the quiz. You work in class or you work online, whatever the case may be. Then you stop work after 15 minutes, meaning at 10:25, you would stop your work. And then I provide 5 minutes for students to scan and upload their work onto Canvas. And so that's the system I've been using for the last several years, okay, ever since the pandemic. And so the only difference this time would be that students would scan, create a single PDF, but instead of uploading to Canvas, you would upload it to the Pearson website, okay? And the reason is the feature is like a semi-automated grading, which allows me to provide feedback faster to students. Okay, so it's beneficial both ways. It takes up less time and resources at my end, and it provides students with a quick turnaround time regards their feedback. So typically I do Quiz Zero and I just say students upload it for like 1 point, upload it to Canvas, like any PDF that you wish. This time it's a new system. Students are not familiar with it. And so I created this Quiz Zero. Again, short assignment. Enter your name, your date, and then answer the 3 questions in there. Create the PDF, upload it, and then after you upload it, there is something known as pinning process. So you drop digital pins where your answers are located. And I talked about this on Monday also. So there's a 4-minute video. I provided it in the link. Go ahead and review that video. And then understand the pinning process. Once you upload it, you have to drop pins, meaning if I ask you where question 1 is, then you drop a pin there. This is where I'm answering question 1. This is where I'm answering question 2. And then that's it. And I think 5 minutes should be sufficient time. But if it's not, then, then I'll change it. There is no time limit on the quiz. The only thing is the due date. I made it due tonight at midnight. Hopefully students will have enough time to, get done with it. Total time shouldn't take more than 10 or 15 minutes. That's my estimate. Okay. Second announcement is I am scheduling quiz 1 for Friday. So Friday, first order of business on Friday's lecture at 10 a.m. we'll have a quiz. I haven't yet decided how long it's going to be. Typically, the quizzes that I do is always based on the topics that I covered in the previous classes. Since this is the first one, quiz 1 will assess topics taught on Monday and Wednesday. Then the next quiz after that, quiz 2, whether it's like Monday at 10:10 or Monday at 11:10, will assess topics taught between quiz 1 and then Monday. So it's always the previous topics that we have covered. Make sense? Okay. Let's see. Third announcement. Well, third announcement should actually have been the first one. So thank you to all the students who submitted the poll. Several students did answer stating that they had some time commitments previously. And so since there were several students who have the time crunch, I've decided to stick with the 10:10 a.m. start time. And so class will begin at 10:10 and not at 10 o'clock. Okay, so we'll go from 10:10 a.m. to 11 a.m., take a short break, few minutes, and then come back again and complete our lecture till 12 o'clock, right? Okay, so those are the announcements. Oh, one more thing. There are questions about the scan homework, so let me go ahead and pull that up. Let's see. So assignments and grading. Homework is split in two parts. Combined weightage for the homework assignments is 40%. Out of 30% is for the Pearson assignments that you complete. When you Pearson assignments, basically, let's say if it's a problem, Ohm's law, IR, you do scratch work, you do something on paper, right? It's a simplistic problem. Say it's a 6-step problem. You would write out those 5 or 6 steps somewhere on your paper. That would be the assumption on my part. That's what students are doing. What I want students to do is scan that work and upload it. And that is the homework scan and upload. And this is uploaded on Canvas. Okay. Again, homework is split in two parts. You do the online homework, and then the corresponding work that you did on paper or on your electronic tablet is what you would scan as a PDF and upload on Canvas. So 2 submissions for homework, one on Pearson, the other one on Canvas. And quiz submissions are, of course, all on Pearson. Okay. So that's what the scan and upload submissions are. Collectively put together, your homework scan submissions are worth 10% of your overall grade. So again, if students have any questions, please review these instructions. That's on the syllabus under assignments and grading. The due dates for the scan and upload, I have set it to match the due dates for Pearson. As and when we go along on the, over the 5-week session, depending on how fast or slow we cover the material, the Pearson due dates might change. Oftentimes, I might forget or overlook to change the dates of scan and upload. What I'm informing students right now is the due dates for the scan and upload are not critical, are not fixed, okay? If you're late by a few hours or by a day or so, that is fine. As long as the work is submitted, you will receive full credit, okay? That 10%, and I stated this on Monday also, that 10% for the scan and uploads is yours. Okay, there is no penalty on it. As long as the work is done and it's shown and it's uploaded, you get full credit. There is no penalty on that work. Okay, it doesn't have to be, I mean, it has to be neat, but it doesn't have to be like, ultra neat. As long as it's legible and I can, see through the work, I look through it, and then you get full points. No penalties on those. Okay. All right. Any questions from anyone? Questions? Okay. All right. Let's begin then. Yeah. Okay, so the question being asked is that you don't have any proof of your scratch work. What time? Okay. Okay, so if students have done something like this, I will allow it for the first few homeworks right now. We've done the first homework 1, 2, perhaps some students have done 3 also. So I'll allow it for the first 3 homework. So just submit something and then students will receive full credit. Okay. Okay, let's see. Oh, any other questions? So let's do this. Go to Note and talk about power and energy. So we stopped here last, and I guess this would be kind of like 5th. Homework 2, just due yesterday. No, homework 2 was due. Yeah, it was due yesterday, right? It was based on power and energy, and I'm covering power and energy today. So if you lost any points in homework 2, you send me an email and I will adjust your credit. Okay, so I'm letting all students know, if you lost any points on homework 2, the material was not yet covered in class, even though it's based on your prereq assignment. I mean, based on your prereq physics classes. I still have an obligation to cover this. Hey, I'm doing all right. Question? Yeah. Yes, I do. Some of them are online, some of them are site. Yeah.
Really odd thing, a cat showed up in our office this morning. Anybody bring a cat to school that is lost? No? Okay,
That is
sorry.
interesting. Yeah, that's fine. Yeah, the poor cat was yeah, it was I don't know, maybe hungry or maybe searching for its owner, was running around my legs in the morning. And so I was like, couldn't take, huh? Yeah, it's in the office building. Not this building, but the office building, 20A. Yeah. So it says CPAC. So our office student assistant told me that CPAC might be Cuesta's Performing Arts Center. No idea. So let's see. Let's come back. What was I saying? Oh yeah, the homework assignment yesterday. If you lost any points on it, send me an email and I will adjust your credit. Okay. Okay, so the first thing I want to talk about is the passive reference configuration. And the passive reference configuration has to do with passive components. What did I do with my pen? That's weird. Okay, hold on. Let me. Okay, all right. So let's finally begin. Passive reference configuration has to do with passive components. Essentially, it states if current direction enters the positive terminal, power is positive. If current direction is entering the negative terminal of the voltage of the element, then power is negative. And so power equation for electrical engineering, or well, in general, electrical power is given by the product of voltage and current. No matter what element we are dealing with, whether it's a resistor, capacitor, inductor, or a source, electrical power is always the product of the voltage and current. So P equals VI. Now, if it's an element, it's a passive element, doesn't have any energy of its own, the current for a passive element will always enter the positive terminal, right? So if you have an element, let's say A, B, C, D. In element A, we are given that the voltage across element A is plus at the top and minus at the bottom. Okay, so plus at the top and minus at the bottom. So let's use a different color for that. So plus here, minus here. And the current is coming in this direction. It is entering the positive terminal of A. Then power is positive. So the equation we use is P equals VI. P equals VI. Power is positive. Okay. If you look at element C, well, actually, you know what? Let's look at element D. In element D, negative is up top, positive is below, and the current is entering the negative terminal. If current is entering the negative terminal, we say power is negative. And energy is being supplied. Okay, energy is being supplied. So if it's positive, energy is being received or absorbed. And if it's negative, energy is supplied. In general, passive components, resistors, inductors, capacitors are all passive components. They do not have any energy of their own. So it's always positive for those passive components. If you look at element B and C, you can see there's a plus and a minus sign this way. And if you extend the tail end of the arrow indicating the current, you see for element B, the current still enters the positive terminal. And so power is still positive for element B. Does that make sense to everyone? Right? And the same concept also applies to element C. In element C, you have a plus up top, minus at the bottom. And if we extend the arrow, we see it is entering the negative terminal. So power is negative. We use the equation P equals minus VI. All right, let's take a 10-second pause. Think over that. Let me know if you have any questions. And again, online students, I will not be able to monitor the chat window. So if you have any questions, feel free to interrupt. Yes, if it's a source, so the question being asked is negative power would be associated with something like a battery, like a source. Yes. Yeah. So in general, just going off on a tangent a little bit, in general, if mostly all analysis deals with passive reference configuration. There is an active reference configuration also, where the active elements like source is used as the reference, meaning the current entering the negative terminal is treated as positive. I mean, not current. A power for an element where the current enters the negative terminal is treated as positive. And we use that because we are dealing with like power sources and power electronics, anything to do with power and energy, their active reference configuration is more useful. As far as this class is concerned, we always use passive reference configuration. Okay, passive reference configuration can be stated in multiple ways, but the easiest way is if current enters the positive terminal, power is positive, energy is being received. If current enters the negative terminal, power is negative, energy is being supplied. A real life example would be a portable battery or a rechargeable battery. So whether it's your smartphone or tablet or mobile device, or your laptop for that matter, it has a battery in it, electrical vehicle for that matter, EVs, right? If it's a rechargeable battery and you're charging it, it's receiving the energy. It's receiving the energy from the power outlet, it's receiving the energy from somewhere else. So in that case, that battery is acting like a load. It is not a source. Make sense, right? It's receiving the energy. But when you disconnect the charger and you use the energy from the battery, now the battery is acting like a source. And so the battery is now supplying energy. So a rechargeable battery is an example of both a source as well as a load. Okay, 3 straightforward examples. In example A, we have a plus up top and minus at the bottom, and we see the current is entering the positive terminal. So power is positive. We use the positive equation P equals VI. 12 times 2, 24 units for power. Anyone? Watts, and named after James Watt. British engineer, British scientist. And then example B, plus up top, minus at the bottom. So we extend the arrow to see where the point of entry is. And we see the point of entry is the negative terminal. So power is negative. And we use the equation P equals minus VI. And when you're solving these kind of problems, you don't have to do anything except determine which equation we need to use, plus VI or minus VI, and then simply plug in the values as they are given to us. So this would be minus of 12 times 1 results in minus 12 watts. So that would indicate that this is supplying power, it's supplying energy. Okay. Any questions? And then again, one point to note, in real life, power and energy are never negative, right? The plus and minus signs for these quantities are just for us, us humans, for us to balance out the equations, mathematically speaking. If we didn't put a minus sign in our equations, they would never balance out. Law of conservation of energy would not work, okay? Okay, let's take a look at example C. So minus up top, plus at the bottom. If we extend the arrow, we can see it enters the positive terminal. Power is positive. We use the equation P is equal to plus VI, and we plug in the values exactly as they are given to us. So it would be 12 times minus 3 results in minus 36 watts. So in example C, even though our equation states, the equation results in a positive equation P equals plus VI, once we enter the values, we obtain a negative result. Negative result indicates that the power is being supplied. Okay, let's take a pause, think over that. Let me know if you have any questions. Any questions from anyone? No questions? Okay. All right. Let's move forward then. Current law, and then KVL, two of them. How do you say this name? Or how would you pronounce this name? Kirchhoff? Kirchhoff? I'm from India, and so the way we say this name is Kirchhoff. So if you hear me saying Kirchhoff, that's who I'm referring to. So I was in a meeting when I was, a long time ago when I first arrived to the US, and somebody was talking about Kirchhoff. And I was like, why are they referencing Star Trek in this meeting? And it took me a while. It took me a while to realize they were talking about Kirchhoff. But he was a German physicist, German scientist, came up with the two most important laws that applies to physics and electrical engineering. And from what I understand, the modern German pronunciation is Kirchhoff. Kirchhoff. Now, I don't know if that's indeed how it was pronounced back in the day or not. But, again, the German pronunciation is Kirchhoff. But again, if you hear me saying Kirchhoff, that's who I'm referring to. Came up with two laws based on the law of conservation of energy, KCL and KVL, Kirchhoff's current law and Kirchhoff's voltage law. Basically, again, as I said, it's based on the law of conservation of energy. It states that if you sum up the currents around a node, they should all sum up to 0. If you sum up the voltages around a loop, they would all sum up to 0. Now, every student would have their own preferred way or method of applying KCL and KVL. I'm not here to change that. If you're already familiar with these two from your physics classes, from high school, from AP credits, whatever, and if you have a preferred method that works for you, you stick with it. You do not have to do what I do, okay? And so this is what I do. I'll show you what I do. When you have a connection like this, marked by a dot, that is known as a node. A node is an electrical junction point. It's where two or more components are connected together. Okay, two or more components are connected together. Now, current always flows through a wire. Voltage is always across 2 points. So in this case, let's say if we had currents flowing in this direction, right? You have 4 connections at that node. And let's say IA, IB, IC, and ID. The way I apply KCL is absolutely straightforward. I want to write out a mathematical equation using KCL, so I put an equal to sign. And all the currents that are entering the node, I place on the left side, and all the currents exiting the node, I place on the right side. And I simply add them all up. So that way, I don't have to worry about plus signs, minus signs. I don't have to worry about making any error in my equation. And again, if you have a preferred way of applying KCL, you can stick with it. But this is what I do. All the currents entering the node are equal to all the currents exiting the node. If you think of a node as a traffic junction, the traffic junction has like 4 roads leading out of it. Some vehicles are entering the junction. Let's assume they're all one-way streets, right? So some vehicles are entering the junction. The number of vehicles entering the junction have to equal the number of vehicles leaving that junction, right? Otherwise, you'd have Die Hard 4. Anyone seen that movie? Where you have all lights turn green, accidents, traffic jam, right? So that's kind of like the same point. So in this node, we have IA entering the junction, IB leaving the junction, IC is also leaving the junction, and ID is entering the junction. And I have my KCL equation. So again, entering has to equal all the currents exiting or leaving for that matter. And so KCL is, I believe, the homework that's due tonight. KVL, I believe, is due tomorrow. And then circuit elements on Friday. These are the 3 most important laws of electrical engineering. This entire course is based on these 3 laws, okay? Ohm's law, KCL, and KVL. Kirchhoff's current law, Kirchhoff's voltage law. All other techniques that we will learn are based on these three equations. That's it. So I cannot stress enough how important it is for students to get familiar with these three laws and be able to apply these efficiently, quickly, and correctly. Okay. And of course, the fourth one is the power equation. Again, these three are the most important ones. So again, KCL, sum of currents entering the node is equal to sum of currents leaving the node. If you define it in terms of the law of conservation of energy, you say all the currents through a node or through an electrical junction sum up to 0. When you use that definition, you have to put a plus sign on some currents and a minus sign on the others, okay, depending on which one is entering or which one is leaving. Okay, questions before we move on to the example? Straightforward? Yes. Right now, we're just looking at this one. Just this example. So the IA, IB, IC, ID are referring to the illustration I just drew out. And then the examples, of course, is the next one. Okay. All right, so then let's look at this example on the left. Okay, we have 5 elements, A, B, C, D, E. IA is given to us, 6 amps. IC is -2. IB is asked of us. ID is also asked of us. IE is not given, but we'll go ahead and find it anyway. Okay. So which one do you think we can try and solve first? Take a few seconds, take a look at the circuit. Anyone from online? IE is 1, yes. Any others? ID also, yes. IB, yes. But if we try to solve IB, we can apply KCL here at the top, or we can apply KCL here at the bottom, either side of IB, right? And so when you're trying to solve a circuit and you have an element, you're trying to find the current through that element, you can apply KCL to either terminal or either end of that element. Okay, depending on which variables you have, the values for, that is available to you, you can apply KCL at either end of that element. In this case, if I wish to apply KCL to IB, if I look at the bottom node, IE is coming in, ID is coming here. Both of those are unknown to us, so we cannot apply directly. If we apply KCL at the top, IA is coming in, IC is coming in. It is possible because both values are given to us. Even before that, if you look at this node right here, bottom left, this node, you have IA going in this direction and IE going in that direction. So what can we write about IE? Current through a branch has to have the same magnitude. So the value of that current would remain exactly the same. That wouldn't change because this is the exact same branch. Ignore the arrowhead. If you ignore the arrowhead, what is the value of IE? Anyone? I think Roderick just said something. Remember the 2 subscript notation for current. The same current in the same branch can be referenced or noted as, if IA is going in this direction, then we can say minus IA is in the opposite direction. And so you're absolutely right. It is 6. So IE would be minus IA, be minus 6 amps. And then we can do the same thing for ID. ID is equal to minus IC. And so ID is 2 amps. Again, repeating the same thing. Plus and minus is for us humans to balance out the equations. Okay. So depending on whether you're looking at a circuit from one aspect, you would have a positive value. If you look at it from a different aspect, you'd have a negative value. That's all it means. It doesn't mean anything else. Now, the reason you might have a plus and a minus is because as engineers, when you try to solve a circuit, everything is unknown to you. Okay, everything is unknown. So you would make certain assumptions. We don't know which direction the current is flowing. We don't know the polarity of the voltage. We might know the source. And so from there, we can make certain assumptions. But, large complicated circuits, you have to make some assumptions and then just roll with it. So we make assumptions and then we solve the circuit, and it will turn out that our assumptions resulted in a minus or a negative value. Now, all it means is the assumption, the assumed current direction is flipped, or the assumed voltage polarity is flipped. That's all it is. And that's what this is trying to show you. Yes? So we don't have to change it, no. So the question being asked is, what should you do if you solve a problem and your assumption results in a negative value? In class, whether it's the homework or whether it's the quiz or whether it's the exam, if a student obtains a negative value, that is not a standalone. That negative value corresponds to the assumption made at the beginning of the problem. So I would look at both the assumption and I would look at the final value. And if they both match up, then the student receives full credit. So you don't have to change it. But in real life, if you're working as an engineer, then of course, yes, you would change it. But the important point to remember is the assumption taken along with the final value would, should match up. If they match up, then your answer is correct. Student will receive full credit. Okay, any other questions? All right. So then IC is minus 2 amps. ID results in 2 amps. IB, now I can apply KCL at the top or at the bottom. Let's apply it at the bottom. And then I can write IB is entering the junction. So is IE and so is ID. So I can write my KCL as IB plus IE plus ID is equal to 0. Because all currents are entering, they all go on the left side of the equation. There is nothing on the right side, no currents are leaving, which in real life, physically, it's not possible. So IB is minus IE minus ID. Minus IE would result in 6, and minus ID would be 2. So 4 amps. 4 amps. Make sense? Okay. Any questions? Okay, so let me understand. The question being asked is, if we take A and E, yes, they will add up to be 0. Because if you apply KCL at the bottom node right here, so the question being asked was, if we add up IA and IE together, would they result in 0? And the answer is yes. One is yes. One is positive, the other one is negative. So if you sum it up, they will result in 0. Yeah. Okay, Then let's talk about series connections. Okay. And from past experience, I found that identifying circuits and components in series and parallel is where students have some trouble. Okay. So even if you're familiar with it, the point of the circuit analysis here is as soon as you see a circuit, we should be able to identify which connections are in series and which are in parallel. Going forward, when you do circuit analysis, we will make certain modifications to the circuit based on assumptions. So we'd assume something, and then our circuit would change. And if a circuit changes, then the circuit connections change. So a component that was previously in series might turn into parallel or might turn into something else. So depending on the connections, it may be in series, it may be in parallel, or it may be neither. Okay. So series connections, I just like to show this, is when you have two connections, two elements connected together at one node, at one junction. Okay. A and B. Now, series connection has no more than two components connecting at that node. Okay. That node should not have more than two connections. Okay, no more than two connections. And then we can state that the two components are in series between their outer terminals. Okay, so between any two pairs of terminals, there are elements that are connected in a chain with no more than two connections at any single node, then they are said to be in series between those two outer nodes, between those two outer terminals. Series connection can apply to an unlimited number of components. Okay, so you could have a million components, a billion components, all connected in series, as long as they are uninterrupted. They're all set to be in series between their outer terminals. A real life example of this is your holiday decoration lights or Christmas lights. Old designs, there used to be light bulbs all connected in series. And you would plug this into your power outlet, right? So this power outlet, not power outlet, sorry, power plug. Okay. And these light bulbs would all be connected in series. Your current would be flowing in one direction, and they would all light up. Now, the problem with the series connection is if one of the lamps or the light bulbs blows out or the filament is blown out, then the entire connection is broken. If the connection is broken, nothing works. Okay. So that's a real life example. Now, modern, once they realized that this was a problem, they decided, they stopped using this kind of design and they combined, certain sections in series, and then multiple sections will be connected in parallel. And that's how modern light bulbs are. So even now, if you pick up, depending on, relatively inexpensive, relatively cheap ones, if one light bulb blows out, it'll turn off only like maybe 5 or 10 light bulbs in those series. The rest of the circuit would work fine. And the reason is because it's now connected in parallel, not in series. So that's a series connection. If we take a look at the circuit up here, this circuit, can you identify which elements are in series and which are in parallel? Any guesses? So the answers are correct. A and E are connected at the bottom node, which is right here, right? One single connection between A and E. There is no other connection at that node, only two components. And so we can say A and E are in series between these 2 points. So let's note this down as 1, 2, 3, 4, 5, and 6. Okay, so A and E are in series between nodes 1 and 5. And then D and C are in series between nodes 2 and 6. Okay, nodes 2 and 6. And there's one other important point I'm also going to make in just a few seconds. But does everybody see that series connection? Let's take a 10-second pause and then think over that. Let me know if you have any questions. Yes. So the question being asked is about components in parallel, and the answer would be no. And again, as you said, we haven't gotten to it yet, but so when we get to it in a couple of slides, I'll talk about the parallel connections. There's one other important point I need to make here before we take a break. So any other questions before that? Okay, so if you look at 5 and 6, what do you see? Node 5 and 6. There is no component connected between 5 and 6. There's only a wire. And if there's only a wire between two nodes, it's the exact same electrical node. 5 and 6 essentially are the same node. They are not different nodes. If I was solving this, I would not label 6. I would just state that that is 5. Okay, so if you have two nodes, like 5 and 6 labeled here, and there are no components connected between those except for a wire, the wire is making a connection from here all the way to D. It's the exact same electrical node. A real life example would be an extension cord. The bright orange ones that you may have used, you might have used like a power strip. Is a power strip like right here. You plug in that extension cord into a power outlet. What would you expect to happen? Even if it's a 100-foot long cable, you would expect, and you plug it into the wall there, you drag it 100 feet away, you would still expect 110 volts to appear at the other end of the power extension cord, right? So electrically speaking, the 100-foot distance is immaterial. Even in real life, 100 feet away, we expect the exact same voltage and current to appear at the end of that power extension cable. It is the exact same electrical node as the power outlet. So it doesn't matter how long it is. In real life, it does matter because long distance would render higher resistance. High resistance would result in voltage drops. Okay. In theoretical circuit analysis, everything is ideal. Ideal components, ideal wires, ideal conductors, ideal resistors, ideal capacitors. When I say ideal, it means that if you have a 10 ohm resistor, that resistance value is 10 ohms. It is not 9.99, it is not 10.01. In real life, if you take a resistor box, and you measure the value of the resistors, you will measure 9.98, you might measure 10.05. But ideal ones in circuit analysis, it's always the fixed value. When it comes to conductors and wires, ideal wire or ideal conductor, the resistance is always 0 ohms. Doesn't matter how long you draw the wire. The wire could be a dot. It could be a dot, small dash, small line, or a really long line. They're all 0 ohms. Hence, electrically speaking, they are the exact same node, no difference. All right, let's take a break. It's 11:03. Let's say a 3 to 4 minute break, and we'll begin at 11:07, 4 minutes. And again, as usual, I mean, if you know, while I'm talking, if you need to leave the room, that's absolutely fine. You don't have to ask permission. You don't have to do anything. Just walk in and out as you wish. Yeah, go ahead. Yeah, it might take longer than 4 minutes though. Yeah, it's you all know where that building is, 20A. You can walk down. So you walk down here and you just make a right before the double doors, and then you walk out of this building, and it's like right in front of you.